What if the universe you wake up in, the sun on your window, the city you know, the life you live, is just one bubble in an ocean of bubbles? Tonight, we're going to take that wild idea seriously. Not as science fiction, but as a set of scientific proposals that physicists are actively debating and testing. The word multiverse actually covers several different concepts. To keep things clear, we'll follow a simple roadmap. 4 levels of multiverse laid out by physicist Max Tegmark. Each level asks a different question about what everything might mean, how it could come to be, and whether we could ever know it's true. Level I is the humblest and the most straightforward, different regions of the same space. Our best cosmological measurements tell us that space is extremely close to flat, and if space keeps going without end, then everything that can happen will happen somewhere. With infinite space, particle arrangements repeat. That doesn't mean there's a parallel fantasy world down the block. It means that beyond the limits of what our telescopes can ever see, there could be whole regions of spacetime that are essentially identical to the portion around us, even down to a planet that's a near copy of Earth and perhaps someone who thinks they're you. The reason is simple: a finite volume of space, like our observable universe, can be in only a finite number of distinct configurations. If the cosmos is infinite, those configurations must repeat, sooner or later. This idea is an extrapolation of ordinary cosmology. It follows from the cosmological principle that the universe is homogeneous and isotropic on large scales, plus the possibility that space is unbounded. Level I is wild, but it's not metaphysical. It's a straightforward consequence of accepted physical laws extended to the largest scales. And crucially, it's the easiest of the multiverse ideas to connect to observation. Measurements of the cosmic microwave background and of cosmic curvature can give us clues about whether space is effectively infinite or not. Level 2 ups the stakes. Here the picture of reality comes from cosmic inflation, a period of exponential expansion in the first tiny fraction of a second after the Big Bang. Inflation explains a lot: why the universe looks flat, why the cosmic microwave background is so uniform, and why there are tiny fluctuations that later grew into galaxies. But many inflationary models suggest inflation didn't stop everywhere at once. Instead, space could keep inflating in some regions, while other regions exited inflation and settled into the kind of hot, expanding universe we inhabit. The result is a froth of pocket universes, each forming its own bubble in an ever-inflating background. Those pockets might obey different low-energy physics. They could have different values for fundamental constants, different particle types, even different numbers of large spatial dimensions. That's where the multiverse starts to intersect with the problem of fine-tuning. The constants of nature, the strength of electromagnetism, the mass of the electron, the cosmological constant, appear to lie in a narrow range that allows atoms, stars, and chemistry. One explanation is that there is a vast landscape of possible physical laws across different pockets, and we simply find ourselves in one of the rare pockets compatible with observers. That line of reasoning is called the anthropic principle. It's useful to some scientists. It makes a quantitative prediction for things like the cosmological constant. It makes other scientists uncomfortable because it changes the type of explanation we seek. Level 3 comes from a completely different corner of physics: quantum mechanics. In 1957, Hugh Everett proposed a radical way to remove the special role of measurement from quantum theory. Instead of the wave function collapsing when a measurement is made, Everett suggested the wave function always evolves unitarily. The result is branching. Whenever quantum possibilities exist, the universe splits into non-interacting branches, each realizing one of those possibilities. This is the many worlds interpretation. In practice, that means every quantum event, every decay, every photon hitting a detector, every uncertain decision at the microscopic level produces a branching where all outcomes occur, but in different branches. The math of quantum mechanics remains unchanged. What changes is our picture of reality. Decoherence, the process by which quantum coherence is lost to the environment, explains why these branches do not interfere in everyday life. Decoherence turns an initially philosophical idea into a technically precise framework one can use to track how classical-looking worlds emerge from quantum mechanics. Many worlds is elegant in its own way, but testability is subtle. The interpretation makes the same experimental predictions as standard quantum mechanics, so it's not easy to distinguish on the basis of lab results. Its appeal is conceptual. It removes the need for a special collapse postulate and provides a clean, deterministic quantum picture. That said, it forces us to rethink what probability means when every outcome happens somewhere. Philosophers and physicists have tried to derive the usual Born rule, the rule that gives the probabilities of measurement outcomes from decision theory and rationality arguments. Progress has been made, but debates remain. Level IV is the most abstract and to many the most provocative. Tegmark's mathematical universe hypothesis argues that every mathematically consistent structure exists physically. Under this view, our universe is one mathematical structure among a grand plenitude. The laws of physics are simply the mathematical description of that structure. If another consistent mathematical structure exists, it corresponds to another universe. That's an extreme form of Platonism. Math doesn't just describe reality, it is reality. Level IV pushes hard at the boundary between physics and philosophy. It's elegant and sweeping, but it is also the hardest to test. What would count as evidence for or against the existence of other mathematical structures? Can a purely mathematical claim be subjected to empirical scrutiny? For many scientists, Level IV sits uncomfortably close to metaphysics. For others, it's an audacious attempt to answer the deepest question: why these laws and not others? So where does that leave us in terms of science? The core scientific criteria are testability and predictive power. Level I is the most conservative and the easiest to connect to observation. If space is truly infinite, that will show up in precise measurements of cosmic curvature and in the structure of the cosmic microwave background. Level 2 is tied to inflationary physics, and some versions could leave observational fingerprints, specific patterns in the microwave background, or the rare signature of a collision between bubble universes that might show up as a circular anomaly. Those signatures haven't been definitively seen, but the search continues. Level 3 reproduces standard quantum predictions, so it's experimentally indistinguishable from other interpretations for practical purposes. Its strength is conceptual coherence rather than new measurable effects. Level Phi is farthest from empirical testability and slides most readily into philosophical territory. There are real scientific successes that lead some physicists to take multiverse ideas seriously. Steven Weinberg used anthropic reasoning decades before the multiverse became fashionable to explain the small but non-zero observed value of the cosmological constant. His argument showed that if the vacuum energy were much larger, galaxies never form, observers wouldn't exist to measure it. The observed value is compatible with this selection effect. More recently, string theory's landscape, the enormous set of possible vacuum states that string constructions permit, provides a concrete framework for a Level 2 style multiverse. Leonard Susskind and others argued that the landscape makes the anthropic explanation a live possibility. But there are deep problems. Infinity is a tricky business. How do you define probabilities when the ensemble of universes is infinite? The measure problem arises because different ways of slicing the multiverse give different answers for how likely any particular observation is. This ambiguity can produce paradoxes like the Boltzmann brane problem, where random fluctuations producing isolated observers could dominate the population of observers in some measures, making our ordered universe improbably rare. Physicists have proposed various ways to regulate these infinities, cutoffs, causal patches, scale factor measures, but no consensus exists. Beyond the technical debates, the multiverse raises profound philosophical and emotional questions. If every possible outcome happens somewhere, what does that mean for choice, meaning, and identity? Does our life lose uniqueness? For many, the answer is no. Even if other versions of you exist in distant, causally disconnected regions or in different branches, your experiences here remain real and meaningful. The multiverse can feel both humbling and liberating. It expands the stage on which reality plays out without necessarily diminishing the significance of your own role in it. So where do we go from here? The path forward is a mix of better questions and better instruments. Look for signatures of inflation in the cosmic microwave background. Develop more precise tests that could rule in or rule out specific inflationary scenarios. Continue refining quantum theory and quantum gravity because a deeper theory might favor one interpretation over another. Search for traces of bubble collisions or other exotic relics, and work on the measure problem. Clarify what probability means in an infinite ensemble so that multiverse theories can make clean, falsifiable predictions. The multiverse is speculative, yes, but it's also an increasingly rigorous frontier in cosmology and fundamental physics. It forces us to examine what we mean by explanation, by law, and by existence itself. For some scientists, it's the next step in a century-long expansion of perspective. For others, it's a provocative hypothesis that remains to be tested. Which of these levels do you find most plausible? The unimaginably large repetition of Level I, the froth of pocket universes from inflation in Level 2, the branching realities of Level 3, or the mathematical plenitude of Level 5? Tell us in the comments which idea moves you and why. If you enjoyed this deep dive, like the video and subscribe for more explorations of the big questions. Click the next video to go deeper into cosmic inflation, or pick the video on the many worlds interpretation if you want to follow the quantum trail. The universe we know is vast and strange, and the more we learn, the more astonishing the possibilities become.